All right, we are back. This is Tech Math 2. We are looking in the red book. We're on page 34 in the red book, 1.9. So the definition of a degree. So degrees, there's 360 degrees in a circle. That actually comes from ancient Mesopotamia, I think also known as the Babylonians. They had a base 60 number system. Like we have a base 10, meaning that there's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That is 10 distinct symbols. There's 1 through 9 and then 0, that's 10. So base 10 means that's how many symbols you have before repetition. So the next number in our system is 10, which is a 1 and a 0, and then 11, which is a 1 and a 1. And so we start reusing those symbols again. And so we're a base 10. Lots of societies are base 10 because of, 10 fingers. There's been, base 9 societies because women were pregnant for 9 months. Base 12 societies because of the lunar cycles. There's 12 lunar cycles in a year. There's a lot of different number bases that go like that. But the Babylonians were base 60 and good timekeepers. So if you ever wondered why are there 60 seconds in a minute and 60 minutes in an hour, you can thank the Babylonians for that. We're base 10, so if we would have figured out time better, we would have used 100, so if I said a half hour, it would then be 50 minutes. Since now I say half hour and it's 30 minutes, that's half of 60. That base 60 was also why we have 360 degrees in a circle, because they basically broke up a circle into 6 pieces, being 60 each, so 6 times 60 is 360. So that's where the 360 degrees in a circle actually came from. It's quite old. So I bet you didn't know this was going to be a little history class. All right, so now, when we are talking about a circle, we have the center of the circle, and then an angle that is created by the center, where the center is the vertex of an angle, and the sides end on the edge of the circle. That is called a central angle. Central angle. So a central angle is any angle whose vertex is on the center of a circle and whose edges land on the circle. So there is what's called an intercepted arc, and we have major arcs and minor arcs. So if I say angle MOP, MOP, that's this angle right here, that's the central angle. Then the intercepted arc would be right here. When it's a minor arc, you only need 2 letters, MP. That way you went kind of the short way, from this to that. MP could also be made by going the long way, right? That would also be MP. That's called a major arc. Anytime you identify a major arc, there has to be 3 letters. Minor arc is 2 letters, okay? So like angle MOQ. MOQ, that would be right here. That's the central angle. And that's a minor arc. So that would be this arc, MQ. So again, just 2 letters. But if they wanted POQ, POQ, oh no, that's also a minor arc. So that would just be this one, which would just be PQ. So tell you what I'm gonna do. Let's pretend like they asked a tougher one for a major arc. What if they would have wanted us to identify QOM? So this isn't in your book, but let's just pretend they said QOM, but they wanted it as a major arc. QOM, so they want it this way. QOM, but they want this. So if I wanted to identify that major arc, the bigger than 180, we would identify that as QPM, and we'd still put the little arc sign over it. All right. So in this one, they only ask for minor arcs, but they can ask for a major arc, meaning you're going along the wrong way. And so really, it has to identify it as a major arc or a minor arc, because we could have just said QM, and that would be the one that we identified there. So they actually did ask this, MOQ, but they wanted us to just identify the minor arcs. If they would have said identify the major arc defined by MOQ, it would have been this. All right? Okay, let's look at radians. So the definition of a radian. So instead of degrees, we also have things called radians. And you can convert 1-to-1 a radian to a degree. There are 2 pi radians in 360 degrees, or 1 pi radians in 180 degrees. So those are equivalencies. And so we can convert from degrees to radians, radians to degrees. In simplest terms here, where the origin of it came from, if you take a look at page 37 in the red book and 103, take a look at problem 103, they give you theta is equal to S, that is arc length, over R, that is the radius of the circle. So that's arc length, that's radius. And this is the measure of the central angle in radians. So the way they calculated radians initially was they would measure the arc length, actually physically measure the arc length, measure the radius, physically measure the radius of the circle, and then divide the two. And that would give you the radian measure. We usually use this formula, but in a different way. We say arc length is equal to, if we cross multiply, you got 1 times S is equal to theta times R. And that's how you find arc length. So if I have the angle, the central angle in radians, and the radius, I can multiply those two and find the intercepted arc. All right? But so here they have a couple of examples. Angle fog is, here, let's draw it. We got FOG. And they tell us the intercepted arc is 20 feet and the radius is 10 feet. So if I wanted this central angle, that theta would just equal the intercepted arc, which is right here, that's 20, divided by the radius of the circle, that's 10. That's also 10, I only marked it in one spot, but remember, the circle is a set point equidistant from the center. So if you go from center to edge, it's going to be the same length no matter what. The radius is identical no matter what point you choose on the circle from the center. So 10, and so that's 2 radians. Now, we could figure out how many degrees those are. We could multiply it by 180 divided by pi. And figure out an approximation for degrees, but that's coming up next. I'm getting ahead of myself. So here, let's take a look at 105 really quick. So this is just sort of the foundation of where these came from. So again, they have a circle that's given, the radius is 5, and the intercepted arc, they tell us, is 20. So then to find the central angle in radians, you just take 20 divided by 5. And that would be 4 radians. All right? Okay, so let's look at radians in terms of pi. That's 111. And I want to skip to 1.11, and then also 111. Copy that sequence, huh? 1.11, 111. They've got pi over 3 radians is how many degrees? And they have pi over 4 radians is how many degrees? And they have pi over 6 radians is how many degrees? And so what you do, remember, there's a branch of mathematics called stoichiometry. That's when you multiply by essentially 1. Remember, 1 times anything is that anything that you started with. That's called the multiplicative identity. If I take 73 times 1, that's 73. If I take negative 500 times 1, that's negative 500. Anytime I multiply by 1, I get what I started with. All right? Basically, what I'm doing is I'm multiplying by 1, but kind of like a fancy one. So look, I want radians to go away, and I want degrees to stay. Well, if I know there's 180 degrees in pi radians, that's equivalent. That's like 180 over 180, only instead of 180 over 180, I changed the label. So from degrees, I made it radians, and that's equivalent. That's equivalent to 1. And so what's going to happen now is I'm going to cancel the radians, and then I'm going to cancel the pi's. Remember how you multiply. If I want to not cancel, if I wanted to multiply and then reduce, I would take top times top, bottom times bottom. That's how you multiply fractions no matter what, all the way back to the very beginning. So pi times 180 is 180 pi, and that would be degrees, over 3 times pi is 3 pi. And now look, I have that times pi, I have that times pi. Since they're being multiplied, I could divide them out, reduce them, or cancel them, whatever way you want to look at it. I could also reduce this by 3, top and bottom. Or I could say 180 divides evenly by 3. That's another way to look at it. That is 60 degrees. So pi over 3 radians is exactly the same. Not even kind of like equivalent, like you don't have to, it's not about, it's not approximate. This is exact because 3 went into 180 exactly. And so we ended up with 60 degrees. Those are equivalent. Pi over 4 radians. So again, if I multiply, remember, where did 180 come from? It was 2 pi radians is equal to 360 degrees. So you could reduce by 2. I could divide both sides by 2, and then pi is equal to 180. So that's where that came from. So let's see. I've got 180 degrees over pi radians. And again, the radians cancels radians. I got 180 pi degrees over 4 and pi times 4, 4 pi times 180, 180. And so now the pi's cancel off or divide out. You divide both top and bottom by that. Let's see, half and half. So divide by 4, top and bottom. That's 45 degrees. So 45 degrees is the same as pi over 4 radians. And that does, if you're more of a visual person, that does make sense. If you think about it, 45 degrees is half of 90. So look, 45 degrees, 45 degrees, 45 degrees, 45 degrees. 1/4 of 180 degrees. Pi is basically 180. That's another way to think about it. If you don't like this, I like doing the stoichiometry thing because we've all worked with fractions at one point or another. When you had to find a common denominator, you multiply top and bottom by the same thing. So this works better in my brain. Another way to think about it, if you don't like the whole multiply and cancel thing, what you can do is you could do a substitution. So I'll do this one as a substitution. Either way is fine. But here, back to this. Look, pi is 180 degrees. 1/4 of that would be 1, 2, 3, 4. If you split it into even pieces of 4, you would have 45, 45, 45, 45. And so that's why pi, 180 degrees, divided by 4 is 45 degrees. Okay? So just a different way to kind of look at it. If the visualization screws you up, then don't worry about that. Now look, I said 2 pi radians equals 360. I also said that pi is equal to pi radians is equal to 180 degrees. So instead of multiplying and canceling stuff off, this is how I'm used to it. This is how I'm mostly going to demonstrate it. But I have had students go, no, you're making it harder. Just say pi radians. Pi radians can be replaced with 180 degrees over 6. And there's no canceling or anything. I just took pi radians because pi radians is equivalent to or equal to 180 degrees. And I replaced it. I substituted out from radians to degrees. Also, a way you can do it and then reduce. So divide both top and bottom by 6. And you get 30 degrees. All right. Okay. Let's take a look at 116 on the same section. And so we have 90 degrees is how many radians? We have 120 degrees is how many radians? And pi over 3 radians is how many degrees? So we already did these two, pi over 3 radians and pi over 4 radians. So the last two on on 116, we did. There's pi over 3, there's pi over 4. So we already know those. Those are 60 degrees and 45 degrees. Going the other way, we could say 90 degrees over 1 times, and now if I want to get rid of degrees and replace it with radians, I would say pi radians over 180 degrees. And check it out. The degrees will cancel with the degrees. End up with 90 pi over 180. And that's in radians now. And now I have to reduce it. So think about how you reduce. The zeros can cancel, divide by 10 top and bottom. So you have 9 pi over 18, and then divide top and bottom by 9. So I end up with 1 pi over 2. So pi over 2 radians. You can put the 1 there if you want or not. So pi over 2 radians. How about the 120 degrees? Same deal. 120 degrees, multiply it by pi radians over 180 degrees. And so basically what I'm doing is I'm attaching a pi, and then I'm reducing 120 1/80ths because the degrees canceled off. So it is in radians. So what is that? That's 12 over 18. And then what? I can go by 6. Divide top and bottom by 6. So I end up with 2 pi over 3 radians. All right? So I think it's easier to always think of it as you're multiplying by either 180 over pi or pi over 180. Okay? All right. I think, yep, that's 20 minutes. So the next, we'll be doing 112 through 118 next.